Hello and welcome everybody to my talk at this year's AGU. I would like to present you about how to discover an unknown mega-landslide in the Siberian Far East. I'm I.Nitze from the Alfred Wegener Institute in Potsdam in Germany, alongside with Hui Tang from the GFZ in Potsdam and Guido Grosse. And here I'd like to present you how I discovered a massive mega-landslide in the Siberian Far East, which is undocumented so far. But first, I would like to give you a little bit of background. I'm mostly working in permafrost regions, so I'm a remote sensing scientist, but also with a geographic background. And my main job is to map permafrost landscape changes. This includes certain landscape dynamics, such as permafrost thaw. And one of the main features or interesting features in permafrost are retrogressive thaw slumps, which are mass wasting processes which are triggered by ground ice thaw. They look similar to landslides, which you can see here in the images, one from Alaska and one from Siberia. But they are kind of more slow and gradual processes, so they're growing over time, but they're still similar to typical landslides. And I'm mostly using remote sensing time series to map these features and use Google Earth Engine, which is a freely available cloud processing platform for remote sensing data. So now I'm coming to a little background of how I discovered it. So here I'm mostly using Landsat time series. Landsat is one of the longest satellite constellations in orbit already. So in many areas it's since the 70s or 80s. And in Siberia, there are data mostly since end of 90s, around 2000. And here's an example from the Lena Delta in northeastern Siberia of a typical permafrost landscape with a lot of lakes, but there are also some other features like water and rivers, etc. And this is an image from 2000. Here in 2007, we already see a draining lake, which is one typical land surface change which we can find in permafrost regions. So there is a transition from a dark water surface to either bright open soil or already vegetation. And in the third image, there is even more progress. And we take these types of information, the brightness, the vegetation, and the wetness, and these changes over time. So we create a simple trend analysis on a lot of input data, all the input data which we have, typically from summer in that area, and take the trend or the spatiotemporal change of the brightness, vegetation, and the wetness. And we processed more than 100,000 Landsat images for large parts of the world. And in the end, we have an image like that, where we see typical colors for specific landscape dynamics. So for example, lake changes appear in yellow or orange, or other changes like coastal erosion, which we see here on the top right, appear blue. Here are some large-scale examples. So on the left, we see a nice drained lake, which is a very, very typical process that we see in a lot of permafrost regions. So there we see a drastic change, and we can directly grasp that there is a change in landscape. And due to the color, we already can infer what really happened there. On the right-hand side, we see some retrogressive thaw slumps, so these landslide-like features here in northwestern Canada. And the blue signature gives us already the information on what happened. So there's a transition from a green tundra surface to a muddy, wet slump floor. And the orange already gives us an indication that there is a stabilization of the thaw slump, so there's already some vegetation growing. And that also works for landslides. So here's a link to an app that I created. So there you can browse through most parts of the world to check out the data and the maps that I showed you the slides before. And I had a talk about that in last year's AGU, so maybe you can access that as well for more background information. So this here is the main window, the starting page of the Trend app. And now we can scroll around. So it starts in Europe, but we can browse around through the entire world. It has a satellite background map. and the trend layer overlaying over that. It loads pretty quickly. And so I'm typically browse around, look into certain areas. Here, this is Eastern Siberia. There we see a lot of colors which are typically wildfires. So they're pretty large, they have a distinct shape. And so I'm continue to browse around. There are also some smaller fires, which we see in most places here, like here. But then I found that one. This looks pretty weird, and it's not a wildfire. So I looked a bit more deeply into that. And I thought, hey, that looks like a landslide. Now that we found this pretty big feature, I analyzed, okay, and I looked more in detail, what could that be? And it looked like a landslide to me, and I really found one. So here I acquired some or got some satellite imagery from end of June and early July from 2017, and found that that was a pretty big landslide. And there was actually a second one. So the big landslide covered an area of more than 3.5 square kilometers. And there are also the small one, which covers zero 0.3 of a square kilometer. And the big one occurred in summer, must have occurred in 2017, and the small one in summer 2015. And it's located in the Kamchatka region in eastern Russia, northeast of the Kamchatka Peninsula. And one pretty good thing that we have in the Arctic, or working in the Arctic as a remote sensing scientist, there is a DM called the Arctic DM. And this has a spatial resolution of 2 meters and has also multi-temporal capabilities. So we have up to several observations and up to several image acquisitions of the digital elevation model. And the earliest are, I think, from 2011, but we also have several, or we have observations before and after the landslide. So we can do DM differencing and calculate the volume. Here we see 3D models of before and after the landslide. Even before, we already see big cracks here on the top of that hill, and we already see here also the old landslide. So this looks pretty unstable, and then at the end resulted in that massive landslide, which we see here on the right-hand side. We see that the entire top of that mountain slid down into 2 different regions, into this small valley here on the side and into the main valley here on the ground. The distance from the top of the mountain to the valley is 2,500 meters, and the elevation difference is around 250 meters from the mountain top to the valley. And here we see a visualization of the lost elevation. So in red, we see a large loss of elevation. And in bluish colors, we see the deposition of the debris, which we see here in this valley here on the side, which was filled, and also the main valley here on the ground on the bottom. Here in this slide, we see the 2D view of the landslide with the cross-section from south to north, which we will see in a few seconds. Generally, as I said before, the area that the landslide covered was 3.66 square kilometers, and the small one is 0.31. The volume that we calculated is about 20 million cubic meters, or 1 million cubic meters for the small one. So that's pretty big, and it's really one of the bigger ones in recent history. As a comparison, this is bigger than the Oso slide, which occurred in the northwestern US, but quite a bit smaller than the Tan Fjord slide in Alaska. But that still shows that there is a lot of landscape dynamics, especially in cold regions, where which we have to look at. The date occurred between the 23rd of June and the 5th of July 2017. There is no imagery between that available, so there are no optical data, neither radar data. The direction we can see here. In red, we see elevation loss, and in blue, gain in elevation, which means there is deposition of debris. Here on top, we see definitely a large elevation loss, That went into two directions, one to the small valley here to the west and to the main valley here in the north. And that caused a blockage of these valleys, which led to two small lakes, which are still apparent in that region, even in this year. And here we see the cross-section from south to north, where we see in orange the loss of elevation, and in blue the increase in elevation, where we see nicely the erosion part here on the top. And in the valley, we see the deposition of the debris. Let's go to the causes and effects. What are the likely causes of this landslide? We have unstable ground, so there are signs of previous landslides. We saw in the 3D model that there are also some big cracks and crevices. And we see also the structure of the slopes. So here on the north-facing slope, which is the slope of the landslide, we see already perhaps here some debris that was deposited here before, and it's not homogeneous, as opposed to the opposite side, where kind of the structure of the slope is pretty homogeneous. The second one is permafrost, or the boundary of permafrost. So we have modeled ground temperatures of around 0 degrees here, which means that there is likely a loss of permafrost, warming temperatures, and also enhanced freeze-thaw cycles, which can cause the rock to crack a lot more because of the expanding water. So that's something we have to look at, especially in Arctic regions. And there was also seemingly a significant rain event from the 30th of June to the 5th of July. According to the ERA 5 reanalysis data, we have around 62 millimeters of precipitation, but that was perhaps more because there were reports of flooding downstream. And this is a mountain area, so there might have been a lot more. And what's unlikely is that seismics. So this is not a very active area. It ranks quite low on the landslide hazard map, and there was no specific signal, according to personal communication to colleagues from GFZ, who also have contacts to Kamchatka. So there was no significant event in terms of seismics, but also there was no distinct signal from the landslide itself. But the problem is that stations are pretty far apart and there's very little information on that area. So it's super sparsely populated. Fortunately, that's also fortunately because there are no damage or property damage or damage to any people. Okay, so now I'm coming back to the first kind of thing. We saw that this is a super big event that most likely, I haven't heard of any ask around, and I couldn't find any information that this was discovered before. So there might be even more undiscovered processes. There are a lot of small landslides in the Arctic that I already also discovered, but none of that kind of magnitude. So there might be more in some other areas, which are unknown because it's super remote. So there are different methods to tackle that. So one is check your data, check the data on your own. You feel free to discover that the app where you can browse around and look for specific features and signatures. The second one is a more sophisticated approach, is automated mapping. So due to advances in techniques of deep learning or artificial intelligence, it's now possible to automatically scan data for certain features like that. And we're doing that for retrogressive thaw slumps, for example. And there's also another talk that I'm having here in the machine learning session. You find the abstract ID here. And with that, I would like to thank you for listening to this talk, to this exciting topic. You can contact me via email, check out my Twitter and GitHub accounts. And finally, I want to acknowledge my funding sources, the ESA Global Permafrost Project, ESA CCI Plus Permafrost, Helmholtz AI Core, and NSF Permafrost Discovery Gateway. And I thank you, and I hope you enjoyed this presentation.